Hi, it's Miss Adams from Flamingo Math. Today we're going to look at transformations of functions, first beginning with rigid transformations from the parent function. We know that there are 4 types of transformations, either dilation, reflection, rotation, or translation. Anytime we change one of the a values, h values, or k values, that's called a transformation of the parent function. So jumping right in, if you have some function f of x and you add a value to the function, you've vertically translated that function up k units. So we want to think about the rule. What happens on the ordered pair to take the parent function and change it k units up? Well, the x would have to stay the same and the range would change. You would add that k value to the y value. For the translation down negative k units, we're going to keep the x and we would subtract that k value from the y coordinate. Moving left and right, if our argument is x minus h, we would move the function to the right h units. But if our argument is x plus h, we're going to move that argument the opposite direction, or left h units. So this is changing the domain. We would add h and keep the y to move right, but to move left, we would do the opposite. We would subtract the h and keep the y. If you reflect a function across the x-axis, so we're reflecting on the x-axis, we have to change the y. So keep the x value constant and do the opposite of the y for each ordered pair. And then to reflect across the y-axis, we're going to change the x. So the ordered pairs would be the opposite of x and the y stays constant. So we can do this visually. You might want to stop and draw each one of the graphs as we go along. So in the first case, we're going to move the graph k units down, -5. So we're going to go down 5. That changes each y value. In the second one, the argument is x minus 3. So -3 means that we're moving to the right 3 units. So the x's change. We're going to add 3 and keep the y. In the third example, we're going to do 2 things. This one has a negative in front of the 1/2 factor, so the negative would reflect our graph, and the 1/2 factor would compress the graph. So the reflection is -a, that's across the x-axis, -1, and the 1/2 compresses the graph and changes the y value. So we want to change the y. In the fourth example, the negative on the x means that we reflect about the y-axis, so our x's are going to change. So like I said, stop the video and try to sketch each one of those transformations, maybe in a different color. Then come back and check your work. Okay, here's a quick glimpse of my graphs, and hopefully they match your graphs. Moving on, next we're going to look at non-rigid transformations and how they affect the parent function. They're going to distort the shape of the graph completely. In the first one, we have an a value that's going to cause a stretch of the graph called a vertical dilation. In the ordered pairs, we're going to keep the x value and multiply the y value by that a factor. In the second one, we have a fraction. 1/a is our vertical dilation. It's going to shrink by the factor of a. So again, we're changing the range here. We're going to keep the x and multiply by the factor a y, on the y value. The third one, we've got a horizontal compression. It's going to shrink, and the b value is a whole number. So what happens is we're going to divide the x coordinate. We're changing the domain by the factor b, and we're going to keep the y the same. And the last transformation is going to be a horizontal stretch. When the b value is a fraction, we would multiply the domain by the b value factor and then keep the y. And I'm using absolute value in each one of these cases because those values could be negative, which cause reflections like we saw on the first table. So let's jump into example 2. We're talking about the domain of a function. We know that it's between -6 and 8. And we've got to think about what the f function does compared to what's going on with the h function that they've given us here. The h of x takes the f function and it moves the domain 1 unit right. So what's our domain on the f of x? We've got the x of h, the new function, we've got to move to the right. And the domain of f started at -6. The end of the domain, we're still moving the end of the domain 1 unit right for our h graph, but that domain started at 8. So thinking about the domain for our new function, h of x, if we subtract 1 from both sides, the domain is going to go from -7 to +7. This is the domain of our new function. Now think about the range. What affects the range? So the 2 in front of the f of x affects the range, and the -3 affects the range. Whenever there was a multiple of a out here, that changed the y, and -3 on the k value changed the y. And we know that our old range goes from -3 to 7 on y. So what would happen with our range for the h would take the 2, which is the a value, and multiply by -3, but we also have to subtract 3 to get our new range value. So -6 minus 3 puts our new range beginning at -9, and then do the same thing with the other y value. We've got 2 times the original range, but we want to subtract 3 with this value. So 14 minus 3 moves our range from -3, 7 over to -9, 11. This is the new range of the h of x function. Is going to go between -9 and 11 inclusively. Okay. Moving on to example 3, we're going to have a table question here. And the table gives the values for some function k at selected x values. We're trying to create a new function h of x, which is 3 times our k, but we've got this 1/2 x here and a 2. And we want to figure out, based on this table, how do we find the h of 2? So basically, we would just substitute the h of 2 into our rule up here. This is our rule. 3 times the k of 1/2 of this new x, which is 2, and we want to add 2. So following that set of rules, I've got the k of 2 over 2, which is the k of 1, and I want to add 2 to that. So looking at our table, the k of 1 is 3. We've got to do 3 times the k of 1 and add 2. So 9 plus 2 is 11. The h of 2 moves that function to 2, 11. Moving on to the h of 0, Going to do the same thing. Follow the pattern rule. 3 times the k of 1/2 times 0. So that's 0. The k of 0, this is 0. The k of 0 is 4. 3 times 4 is 12 plus 2. So our h function has a value of 0.14. If you want to give these a try, you could turn off my video and try the last two on your own to be sure you understand the process. You can see from my work the h of 10 became negative 10 and the h of negative 6 becomes 2. In example 4, we want to use the parent functions for y equals f of x and be able to describe how the graphs of each of the functions g of x were transformed. We want to state the types of transformations and then be able to graph the function on each of the grids. So we know what x squared looks like, and our g of x is going to have a factor of 2, and then our h value is plus 3 here, so this means the opposite of 3, and then a k value of negative 4. So if you want to make note of that, a is 2, h is negative 3, and k is negative 4. So we know that there's going to be a horizontal translation, and that's going to move 3 units left. That negative 3 moves the graph left. The vertical translation is going to be 4 units down with the negative 4, so this is down. That affects the range. And there's going to be a vertical dilation by a factor of 2. So it's a dilation, it's in the vertical direction, and the factor is 2. And what does that do? That stretches our parent function parabola and makes it thinner with that vertical dilation. And next we want to sketch the curve. So one of the interesting things about our parent function is we know the h and the k value are going to cause the graph to move from 0, 0, because our basic parabola lives over here. This is our basic parabola. And we're going to pick that parabola up and move it 3 units left. That's from here, 3 units left, and 4 units down. But the 2 is going to stretch all the y values. So let's erase this old one. This is our parent one. And we want to move the new parabola 3 units to the left and 4 units down. And we're going to have a stretch factor of 2. So 1, 2, 3. Going to be there. And a nice skinny parabola. Looks like that with a new h and k value that translated from the origin here. Left 3, down 4. In part B, you might want to try this yourself and then come back and check your work against mine. Okay, look with me here on example B. I want to spend a minute on this because knowing what to do to each x and y coordinate really helps in graphing the transformation. Looking at the g of x, I see that we're going to reflect across the x-axis with the negative 1 on the a value, and we're going to also have a stretch factor of 1/2 with the a value being 1/2. The x minus 3 causes a horizontal shift to the right 3 units, and the k value of plus 1 causes us to move the parent function up 1 unit vertically. So this table of values over here in the margin, this is what the parent function values look like for x cubed, -1, -1, 0, 0, 1, 1, 2, 8, and so forth. If you can come up with the rules for what to do with the x coordinates, if you think about plugging in an x, let's say x is 2, 2 plus 3 moves us to the ordered pair 5 for the x, and then 8 was the parent function y value, so half of 8 is 4, and we want it to be negative. So negative 4 plus 1 puts us at the ordered pair 5, negative 3, and you can see that's what happened in my transformation to produce that g of x graph. Having the ability to do this when you're working on practice problems really helps you in understanding transformations and how the domain and range could change with a given set of rules. Let's look at number 5 here now, example 5. We know the domain is negative 5 to positive 5. We know the range is negative 15 to 15, and we're given function g with this set of transformations to take. So we want to describe the transformations and then state the domain and the range of g of x. So first of all, it looks like we have a reflect across the x-axis, and we have a vertical dilation factor of 2. So let's make a note of that. Inside the parentheses, we have a plus 3, so that means that we're going to shift our parent function 3 units to the left. We have a horizontal translation there, so making a note of that. Horizontal translation, negative 3, that's taken us to the left. And I missed this. We also have a horizontal dilation factor right there. So horizontal dilation factor is 3 in this case. So we need to make a note of that. Horizontal dilation factor is 3. And what else? We've got the plus 7. So that's going to be a vertical translation, 7 units up. It's going to go up 7 units. So did we catch everything? Let's see. 1, 2, 3, 4, 5 things. 1, 2, 3, 4, 5. All right, so what's happening with the domain of our g function? So the domain of g is going to have this horizontal dilation factor 1/3, and the x of g, and we're going to move it left 3, and it's got to be either plus or minus 5. So it's got to equal plus or minus 5. So the domain for our new g function is going to go, let's see, where's 5 in here? Give me a second to calculate that. Let's see. So we got the x of g plus 3 is plus or minus 15. So the x of g is plus or minus 15 minus 3. Negative 18. Okay, I just wanted to jot down here what I'm thinking as I'm looking through that. So using this statement here, it's got to be between 5 or negative 5. The domain for g, if we have positive 15 and we're subtracting 3, that means the domain would go to 12. If we have negative 15 and subtracting 3, the domain would begin at negative 18. So I wanted to use this expression to make sure you understood what I was doing. So our domain goes from negative 18 to positive 12. Now let's get rid of that and think about what the range is doing here. So the range is going to be affected by the negative 2 and the plus 7. So thinking about that similarly, the range of g is going to be negative 2, and where's our range? From negative 15 to 15. So the range has to go between positive or negative 15, but we also have to shift that function 7 units up. So shifting 7 units up and doing all of that arithmetic, negative 2 times 15 is negative 30, and add 7 to that gives us the range of G would be from negative 23, and then going the other way, negative 2 times negative 15 is positive 30, and positive 30 plus 7 stops our range at 37. Whew, that hurts your brain, doesn't it? So looking at some important transformations, things to remember here. Transformations that occur inside the parentheses affect the x values, and we do the opposite of the expression. For example, the f of x plus 4 means a transformation in the opposite direction. X is negative 4 or to the left. I like to tell my students it's like taking the argument and solving for the zero of that argument, which lets us know the x is negative 4. And then lastly, transformations that occur outside the parentheses affect the y values of the graph. And we've kind of explored that and learned that along the way. Our last example gives us the h of x. It's a continuous function. It's defined on all real numbers, and we can use the graph to complete the table of h, and that's been done for us. And we want to graph 4 different transformations. The opposite of x, the opposite of h of x. That means we're going to keep the x and flip the y's. So we're reflecting. This is our rule. What are we doing? We're reflecting across the x-axis. So it's going to take that parent graph and reflect all of those. We're going to change all of the y's. So instead of negative 6, it would be positive 6. So at negative 2.5, we're up here at positive 6. At negative 2, we're still at 0. At negative 1, we're at negative 5. At 0, we're at negative 4. And at 1, we're still at 0. At 2, it's positive 4. At 3 is positive 5. At 4, we're back to 0. And at 4.5, we're down at negative 6. So we've got this shape of the graph. Following that rule, keep the x and change the y's. On letter B, we want the opposite of x. So that rule is to change the x and keep the y's. What's happening verbally? We're going to reflect across the y-axis. So sketching that graph, we're going to change the x's. Instead of negative 2.5, we've got positive 2.5 and negative 6. And moving through all of those values, we've got the graph looking like this, reflected across the y-axis. And to save us some video time, turn the video off, graph C and D, and come back to check your answers against mine. And to finish off the lesson, you can see that we have a horizontal compression factor of 1/2, so we're multiplying all the x's by 1/2 or dividing them in half. Keeping the y makes a skinny little graph. And in D, you have a horizontal dilation factor of 2, so we're multiplying all the x's by 2, and it's making that graph stretched way out horizontally on the x-axis. That's the end of day 1 for lesson 12.